for people there.
Yeah, I so used to getting up at the crack of noon.
Well, that's just me, I guess. Okay, today we're very happy to have Julio Parra Martinez from IHES, who's going to tell us about black hole tides and their normalization group.
Okay, thanks a lot, Atul, and thanks for the invitation. It's very nice to come back to Cambridge. My wife was teaching in the art department here for about 5 years. I have very nice memories of this place. Yeah, I'm going to tell you about this work that I've done with these fantastic collaborators. Misha is your neighbor at MIT, and then this like amazing postdoc and student at Princeton, Yuejo and Zihan. And okay, let's just dive in. So the question that I want to address in this talk is, how do we tell apart a black hole from some other kind of mysterious compact object that you might have, some compact gravitating object? But I want to put a description, which a restriction, which is that we can only probe this object with frequencies much smaller than its inverse size. Okay, so we cannot resolve the horizon. We cannot see that it's a black hole. We don't see the darkness. Right? We just have some waves that are probing it, long distances. Okay, so what could this be? Okay, maybe it's just some chunk of matter, like a neutron star or a bunch of coal. Okay, it could be many other things. And why do we care about this question? Well, for what, this is precisely the regime that we probed for much of the evolution of these binary inspirals that we measure at gravitational wave observatories. So especially in this very long inspiral phase, then we have kind of the dynamics of two bodies in GR, and the typical frequencies involved in the interaction between these bodies are kind of 1 over the separation between them. Okay, so that's a characteristic kind of frequency, and then okay, of course, this is much bigger than the size of each one of these objects, except till the very end when they merge. And also the gravitational waves that we measure in our observatories. Here we're looking at distances much further than this. Okay, so even the gravitational waves that we're looking at, the frequencies are kind of much smaller than this, even this inverse size. Okay, so we are in this regime of low frequencies, except very close to the mergers. Okay, and okay, so this deviation, like how do we tell these different objects apart? Well, we tell them apart because of their tides. Okay, so to first approximation in this low frequency regime, we can replace this black hole or whatever compact object that you have by a point particle with a mass and maybe some spin, some angular momentum. Okay, but of course that is not enough, and this must be supplemented by multiple moments that are called the finite size of the object, which are actually dynamical quantities. Okay, so these are not static things. In the previous talk, we saw that these multiple moments can change over time. And we expect that these things are of the order, you know, of the mass times the size of the object to the multipolar number. And then kind of there's a set of quantities which are these love numbers that encode the dynamics of these multiples. Okay, I'm going to first give some like sketch of what these tides are and why they're interesting and what is new that I want to say about them. And then I will try to define them very precisely, and we will compute some of them in GR. Okay, so the simplest kind of these tides are these so-called static tidal love numbers. So here what we study is the linear response of these objects to some external gravitational field, some static gravitational field. Okay, for instance, we ask, what is the induced quadrupole moment of the system? Okay, we applied some external field. So this is some kind of electric part of the Weyl tensor. So this is some external field, it's not intrinsic to the object. And then this can develop an induced quadrupole. And then this coefficient that parameterizes this linear response is the quadrupolar tidal love number. And okay, there's this famous result that actually goes back a while ago to my predecessor at IHES, Thibaut Damour, that the static responses are 0 for black holes in 4-dimensional GR. Okay, and this this is an excellent possible window into new physics, because if you have your favorite theory that will be on GR, generally the prediction will be that these are not 0. But this is kind of just one corner of the story, because there's also dynamical tides, which I'll talk about later, which capture the induced response to a time-dependent external field. Okay, and those are not 0. In fact, it doesn't make sense even to say that they're 0 because of the effect that I will describe.
Do you think it would be possible to measure static response?
Okay, so so these are interesting because they modify the dynamics of the binary, even in the spiral phase. For instance, one can compute how they modify the interaction potential between the two objects. So there's some correction that enters at something which is, for instance, for black holes, is the so-called fifth Possintonian order. So Possintonian perturbation theory is a perturbation theory in Rs over R, or velocity squared over c squared, right? So for instance, you can just compute some correction to the potential between the two objects that it's essentially at 5 p.m. order, but for instance, for a neutron star where this size is 5 to 10 times larger than a black hole, then this can be much larger. Okay, and okay, for the static tides, it's a bit hard to measure, but for instance, for the dynamical tides, for instance, absorption is something that is encoded in the dynamical tides. There's some first bounds already from observations in this paper by my collaborators. Okay, so these are bounds from actual data on these dynamical log numbers, which I'll define later more precisely. Okay, so in principle, yes, we should be able to put bounds on this from LIGO, but I think we don't have good enough statistics really to have some precision.
On the dynamical ones.
So this is a bit easier because the effects on the dissipation, this is on they're kind of more prominent because there is no dissipation without these tides. So it's a bit easier to disentangle them, but in principle also to the static ones. Yeah. Yeah.
So for the static one, you said there is no effect, but if I take two black holes of equal mass and bring them very close, eventually their event horizons will combine. So there should be some nonlinear.
So these are I will define this later more precisely. So these are log numbers with which one can measure from very far away. Right. So they're not these superficial log numbers that were mentioned in the previous talk, which actually a bit harder and more subtle to define. So these I'll define them very precisely in a few slides. But first I want to give you the general picture. Okay. So yeah, my title is Black Hole Tides and Renormalization Group. I already explained what these black hole tides that I'll be referring to. So one in the Earth, am I talking about like, isn't the renormalization group something relevant for like particle physics, like quantum field theory, the running of the coupling constants, or like critical phenomena, right? Like famous work of studying like a critical phase transitions or something about like block spins and how they change at various distances. Well, it turns out that these tidal coefficients, or the tides in general of black holes, or the multiple moments themselves, they run in GR, even in classical GR. And why is that? Because GR is a nonlinear theory, and actually, even for when you have a single compact object, there's an ambiguity in defining the multiple moments. Okay, so we are replacing this object by a point particle when we look at it from far away. And then I need to tell you how much of the space-time that is surrounding the object, how much of the static gravitational field I'm integrating out when I go to this point particle description. Okay, and if you make different choices, say here I have some surface at some radius RC, and then I say, okay, everything inside is what I call the point particle, and then outside is just my power zones, kind of the faraway gravitational field. And then I make a different definition where I take this surface to be a bit bigger, then actually the multiples themselves will change, and generically the dynamical tides will also change. Okay, and this corresponds to.
I guess you haven't defined these quite yet.
Yeah, I will.
But
so yeah,
but if the frequency is if the wavelength is large compared to the size of the black hole,
yeah,
then you should be able to measure from infinity and it won't run.
No.
So an effective field theory description.
There will be an effective field theory description, and then in that effective field theory description, there will be UV divergences, even in classical GR, which will normalize this coefficient.
Okay, but we could do an experiment.
Yeah.
We don't need to know what UV is.
That's right. Yeah. So in an experiment, because we have like
by experiment, we write down some effective action.
Yes. In fact, I will do a theoretical experiment where I'll compute the precise values of this for a black hole in GR. Of some of these dynamical tides, and by a theoretical experiment, I mean, I will compute something in full GR, which is, of course, free of these UV divergences, and then I will go to some effective description where there will be these divergences. And
I guess my question is this running only occur when the wavelength of the perturbation approaches?
No, this running tells you that in physical quantities that you will compute, there's going to be logarithms of the frequency times the Schwarzschild radius or the size of the object, which will be there, and they're kind of the signal that in this effective description there is a running. So there's a physical effect actually that you can measure at infinity that has to do with this running. And I'll show you an observable later where we see these logs and we can resum them using this idea. Yeah. Okay, so all of this is very vague and very big picture. I'll get into details. Yeah.
This radius RC is where you're doing the observation or
No. This is where I'm going to, like, where I decide to cut off the space-time to replace it by a point particle. The observation is always kind of in this far zone, far away from the object. Okay, so I'm telling you that there's some classical running of these multiples that depends on how I define them. So here I'm using the language of particle physics. There's some like UVs, so some renormalization group scale, which is roughly like 1 over the size of this cutoff, right? And there's some anomalous dimension that tells you how these objects change with the size. Okay. So this is a classical question. In classical GR, there's some logarithms that show up in physical quantities that follow this pattern, just like logarithms in particle physics that have to do with some running. But because this is classical, can we understand this running to all orders in perturbation theory, which is something that usually we don't have the luxury of in particle physics? And actually, the answer will be yes, and it's because we found this very nice non-perturbative relation between two quantities. One is this anomalous dimension that tells you about the running of these multiple moments. Another one is a scattering phase shift. So this is the phase shift. Okay, so this tells you how, say, for a black hole or some other contact object, the multiples depend on how you define them. This is telling you the scattering phase shift or scattering a gravitational wave from one object. Okay, so if you compute the scattering phase shift, you analytically continue to negative frequencies, which, okay, for a real scattering experiment, we have positive frequencies, so this might be challenging, say, numerically, but analytically, we know how to do this. And if you take this average, then you can precisely compute this one. Okay, so one of the goals of the talk is to explain this relationship, where it comes from, and how we can use it to say many things. And so there's another insight from this picture, which also comes from ideas of particle physics or condensed matter, which is another essential feature of this kind of renormalization group analysis, is this idea of universality, that we have many different descriptions that at long distances, they become the same, because there's only a few relevant, in the technical sense, couplings that you have in a given theory. So there's only a few parameters that you can tune that really will tell you about the physics at long distances. So for instance, here we have like 2 fixed points. So this one you have kind of arrows coming out, which means that it has some like relevant deformation that will make it flow somewhere else. Whereas this other fixed point only has irrelevant deformation because any deformation you do at long distances goes back to this fixed point. And actually in the gravitational case, it's a bit like that. So only the mass and the spin don't depend on the size of the object. Or don't have this parametric scaling with the size of the object and are well defined at all distances. And these are the only relevant parameters. So there's some universality, and I will write an EFT description and we'll see in which precise sense there's some universality or related to the mass and the spin or the angular momentum. And because of that, we will, by focusing on the case of the black hole, which is kind of the cleanest setting that we can think about, we'll be able to infer properties of this running for generic compact objects and actually even binary systems. Okay, so just to show you that we can actually compute things using these ideas. So for instance, if we do a low frequency expansion, so this epsilon is just GM times the frequency, sigma is basically some dimensionless parameter that tells you about the spin. So we can compute to very high orders. So this is a G Newton to the 6 prediction for the low frequency expansion of, say, the quadrupolar anomalous dimension. And here I just show the universal terms. Okay, there's terms that go like the spin squared, which are not universal, for instance, that everything linear in spin, as I'll explain, is universal. And in fact, this running is the same for a black hole, for a neutron star, for a binary, for the infamous spherical cow that was mentioned earlier. So this is like a prediction from GR that is irrespective of the nature of the object. So the multiples themselves depend on the object, but how they change as you change this cutoff surface is universal. Okay, another goal of the talk is to explain this. Okay, so the outline is the following. So I'm gonna first set up in which framework I'm gonna be calculating these things and explaining the origin of the universality. And I will apply this kind of EFT to computing this running of the black hole. And I showed you a bunch of applications, including to waveform modeling. And then I'll talk about how not only the running, but even the matching, determining the values of these love numbers, we can do using kind of a similar framework and ideas from scattering, et cetera, et cetera. Okay, any questions about the kind of big picture introductory comments? Yes.
Can you explain why the log term is essential for
The what term?
the log term,
The logarithms.
the frequency?
Well, any kind of RG analysis that you know about, its purpose in life is to resum logarithms in some physical quantity. So if you wish, that's what we do when we run coupling constants, yes.
In the language that you're using, would the price tail be logarithmic corrections to quasi-normal modes?
To quasi-normal modes. But this is just in pure GR?
Yeah.
I'm not sure. I'm not familiar with that effect.
So quasi-normal modes are exponentially decayed, and then you have a power law, which looks like a log.
Right. I think those are slightly different because those I think have nothing to do in particular with like the multiple. So this is all like a far zone question. So this is something that you
This is there are far zone. The price tail are far zone.
yeah, but the values of the quasi-normal mode frequencies are actually something that tells you about the near horizon, like the near zone of the black hole. So I think this is a different kind of effect. Yeah. Yeah, because this is, as I mentioned, and I will explain, this is universal. This doesn't depend on having a black hole or a neutron star. So it could be that there's universal logarithmic corrections to some of these things in the near zone, but I don't know. Okay, so let me explain the setup. So the setup is what I usually call the simplest effective theory, where we replace whatever you have, a black hole, mysterious compact object, a Cherenkov hole, maybe you have some stringy setup, maybe this like spherical cow, we replace it by a point particle with spin with corrections. So actually the important part are the corrections. So let me kind of flesh out this. So the leading term is of course just like a Ward line with a given mass coupled to GR. So what does the corrections look like? Okay, so we have a coupling to the spin. So this is the angular frequency in the body frame, which is essentially the spin connection. So the first two terms, actually, there's no free parameters here. We know exactly what the couplings are. And if you tell me the angular momentum, and you tell me the mass, which could depend on time, there's dynamical because there's absorption, etc. Then I know how to couple them. Then there's things like multiple moments coupling to the gravitational field. So this will depend on the multiples of each object. Okay, we have the quadrupole moment, the octupole moment. There's things like spin-induced multiple moments, which are kind of couplings of the curvature to the spin of the object. And these have three parameters. These have some like Wilson coefficient synthesis effective field P, which will depend on the object that you have. But we can power count each one of these couplings. So as we said, this dimensional analysis tells us that these quadrupoles go like m times the size to the quadrupolar number. These spin-induced multiple couplings, they go like the inverse mass. So that basically L over M is kind of the spin length. So they really look like some quadrupole moment or something like that. And here E and B are, okay, I didn't show B, but there's also magnetic couplings of this nature, which are kind of the electric and the magnetic part of the biotensor. Okay.
Are you only doing integer spin here?
Yes.
Because this won't incorporate half integer. This one line won't, right?
No, in fact, this is for a semi-classical object. So the
Yeah.
spin is like a continuous variable.
Right,
Yeah.
yeah.
Okay. So where are these love numbers? How are these love numbers precisely defined in the ZFT? So this is a question that arose earlier. Okay, so there's some kind of classical response function of this quadrupole moment, right? So think about an atom, like the analogous quantity to this love number is the polarizability of the atom, right? And there we have this formula from like our course in optics, which tells us, or in quantum mechanics, that tells us that polarizability is something like the multiple, some transition elements of the dipole moment squared divided by the energies or something like that. So it depends on the dynamics of the system, and in particular the dynamics of the dipole moment. Here it's gravity, so it's these multiple moments. The leading one would be the quadrupole, and then there's some kind of retarded response function for this kind of multiple moments. So there's some classical quantity. So if you have a star, this will depend on, say, the hydrodynamic modes of the star, right? For a black hole, they depend on some mysterious degrees of freedom near the horizon. if we do a low frequency expansion of this object, so causality tells us that this is analytic at small frequencies, we can expand it, and the leading term is a static tide, which is 0 for black holes, and these corrections are dynamical tides. Again, dimensional analysis tells us how each one of these coefficients scale. And then for n even, where n is the power of omega, then we have conservative effects. The odds are complex, so these are kind of dissipation. So these are the dissipative tides, and these are conservative tides. Okay, this is 0. These are not 0. In fact, as we'll see, these cannot be 0 because they run. So you need to tell me at which scale you're defining these things, and so generically it doesn't make sense to say that they're 0. Okay, and there's an equivalent description where you can forget about these multiple moments and just kind of integrate them out, kind of solve for the dynamics, plug it back in. And for instance, for the conservative tides, these would just give you non-minimal couplings of the gravitational field to the world length. So for instance, these static tides, if you just plug this back into the action, then they will give you a coupling that goes like the curvature squared on the world length, or derivatives of the curvature for the dissipative, for the kind of dynamical tides. Dissipation, okay, one needs to do something a bit more sophisticated and use this informalism, but again, it's some effective action that you can write out if you don't want to think about these multiples. Yeah.
So usually, I mean, if we have some effective action with higher dimension operators in it, so the different terms will have different powers of the energy in them.
Yeah.
And we would just think of those as different couplings, right? So
yeah.
We've got one coupling between the quadrupole moment and the energy of the perturbation, and then one to the square of the energy.
Yeah.
Why aren't those just different couplings rather than one coupling running?
They are different couplings. So you see, like this whole series, each one of them is like a coupling.
They were running because it was. Why isn't lambda 2
so
omega
I can
squared?
describe the running of kind of this full object rather than individual terms. I will be able to write an energy equation that tells me about the running of this whole function instead of like each individual piece. So it's just a matter of how you organize your calculation, but it's like it's useful because this is kind of the polarizability, like the frequency dependent polarizability, and we can write an anomalous dimension that depends on the frequency. But yeah, you can think of it as different couplings, and you're just looking at the running of.
And you have some equation that relates different couplings in the there.
Yeah, in fact, that renormalization group equation. Okay, I'll show in a second how this shows up in divergences, but yeah, that renormalization group equation will relate all of these couplings. Yeah.
So just a question
Yeah.
about dissipation, because in this Newtonian limit, the equations of motion are symmetric. There is no dissipation. So here, is it gravitational waves, or what are we talking about in dissipation?
So this dissipation can be just the kind of tidal heating of a neutron star.
No, for empty space, like black hole.
For a black hole, there's absorption of energy and angular momentum into the black hole. Yeah, and that's encoded, for instance, this is the leading, at low frequencies, this number encodes kind of this leading like absorption of energy and angular momentum. Yeah, and you can explicitly compute the flux and see that if this coupling is 0, then the flux is 0 in this point particle description, and if it's not 0, then yeah. Okay, so even without specifying which kind of object I'm talking about, this EFT makes some predictions. So let's go over them. So as I told you, the leading couplings, kind of the mass and the spin or energy and angular momentum, they're universal. There's no free parameters. All of the non-universal terms are things that go like spin squared, or things like the size of the object to the 5th, which is this kind of static tides for black hole. So actually, for instance, this EFT predicts that we cannot tell a point particle apart from a black hole until at least this order. Okay, so if you're looking at it at very low frequencies, it's actually very hard to distinguish a point particle from a black hole, because you need to go to the order where you see these kind of leading operators. So the EFT works extremely well. Of course, for a neutron star, this is kind of much bigger, so it's a bit easier to distinguish from a point particle. But in general, it's very hard to see the difference. Okay.
Could you have guessed that it would be in 5th order?
Well, I guessed it using power counting, so it's just dimensional analysis that tells you that, but I don't know any other way. Yeah. Okay, and the other prediction is that if you do some computation in this point particle EFT, I'll show you an observable in the next slide where this happens, where you have this point particle coupled to GR, you just compute like the dynamics of this thing in classical GR, you will find some inconsistencies. So you will find some UV divergence in the classical theory. Okay, there's some integral that you have to do because you have point sources, so kind of energy is conserved, momentum is not conserved at each source. There's an integral over the momentum of the sources, and then that integral is divergent. Okay, much as what happens in particle physics when you have a loop. So when you compute this observable, I'll show you next slide an example. There will be this divergence, and there will be various logs that have to do with this kind of cutoff or the renormalization scale, right? And then these logs or this running, for instance, if you have a log that is proportional to this tidal coefficient itself, then we will call that an anomalous dimension. If there's a kind of unisolated log, we will call that a beta function. So this tells you that these guys, you can think of them as depending on this cutoff and scaling like this. Okay, so there's this renormalization group running, which is defined in those terms. So you can write an evolution equation for these couplings that relates to this anomalous dimension and this beta function. But this gamma, for instance, tells you about the running of the multiple itself. Whereas, for instance, there's this kind of renormalization group equation that has to do with this beta function where we subtracted the anomalous dimension that tells you about the running of the log numbers. Okay, and all of these things are things that you can compute in the effective theory. That don't depend again on the nature of the object. So for instance, look at an actual observable. So say I have like a dynamical quadrupole moment. So this won't be a black hole, but there's some other kind of, or maybe a perturbed black hole or what have you, or a binary. And then we're computing the kind of radiation that comes from that dynamical quadrupole, just solving Einstein's equations with that, but we're going to do it in this point particle EFT, where the quadrupole is just a dynamical variable on this word line. And then if you just do a computation, you just find UV divergences. So you compute this, so I'm drawing it like here, so it looks like a loop, but the integral here, it's just an integral over the momentum of this source here. Or if you do it in position space, you can write all this but this is just perturbation theory solving to like next to leading order. And you'll find that there is some divergence. So the integral is not well defined.
What are those two lines there? Those are gravitons?
Those are gravitons. So here we have kind of the leading order radiation is just kind of one graviton, which is like one propagator, like one Green's function that goes to infinity from the quadrupole. But then there's kind of nonlinear corrections to that, coming to do with the interactions, like the nonlinearities in GR. So I'm just doing nonlinear perturbation theory at low frequencies. And then, okay, this first one is well defined. So this is going to like not linear order, but next to like the first nonlinear order. But when you go to next to nonlinear order, you find that it's not well defined. Like this point particle description, and it's natural because like a divergence just signals that there's some missing UV information in our calculation. Okay? And this is nothing special to quantum field theory. Like we can have this.
So this is related to the divergent self-energy of the sort of Coulomb-like field.
So this is worse because like that self-energy is a power divergence. So it's another example of a classical divergence that you would have. So these are logarithmic divergence. So that's power divergence is typical, just tells that we have to tune our couplings to the right value that we measure with experiment. But this is a logarithmic divergence that tells us that there's something that changes with the scale logarithmically. Yeah, so it's in spirit similar to the usual like electron, like self-energy in classical ENM, but it's because GR is more interesting and nonlinear, then it also has logarithmic divergences, like the ones that make couplings run in quantum field theory.
So just to understand here, you're keeping the GR part classical and doing loops in the EFT?
No. Everything here is classical. I have a classical point particle coupled to GR, right? But that
point gravitons are not classical objects, they're quantum objects, right?
That's right. So
you have to quantize the
so by these
field.
diagrams, I really mean I'm just doing perturbation theory. So I'm writing box H equals T mu nu plus H squared plus H cubed, et cetera, et cetera. I'm solving that equation perturbatively. I'm just drawing it as diagrams because it's the same as calculating these Feynman diagrams. And yeah.
But there is no H bar.
There's no H bar. There's no H bar anywhere. Yeah.
Guess I was confused with this HL omega equation. You explicitly wrote a black hole on your right and a brown.
Yeah. This is just because I it's this thing when you take the H bar going to zero limit. I'm using this language of expectation values because it's more familiar to some people, but this is a classical calculation in classical GR. Yeah. Of the radiation by a dynamical quadrupole and coupled to the mass of the object. So if you just do this calculation in perturbative GR, you find a nonsensical answer. And you need to regulate the calculation.
So the loops are getting generated just by recursively solving the field equations or something?
The loops
You
are
can-
because you have bulk vertices where energy and momentum are conserved. And then you have couplings to the world line
Right,
because you're only integrating over time, then only energy is conserved. So you need to integrate over the free momentum.
oh, you don't have.
And then
multiple-
those integrals are divergent.
Okay,
And position space is just the usual like point-like singularities that you find in position space when something hits the point particle.
I see.
In the diagram below, M is the mass.
M is the mass, yeah.
So you have a graviton coupling to the quadrupole, but then how can graviton couple like?
It's just this coupling is a leading like coupling, like a minimal coupling of a point particle to GR. This yeah, just the usual like Nambu-Goto like coupling. Yeah.
So if we were to do a much more complicated calculation where we start with a little point like of a black hole,
Yeah.
we'd never encounter it.
That's right. For a black hole, you will never encounter that, but you will find that there is this log in the answer, where you would have omega times RS inside of the log. So the log is physical, and RS is the UV cutoff. So the log is physical. You won't have that divergence, but there will be a log, and then this RG will actually help me resum this log, and I'll show a formula later where I resum all of these logs coming from these sort of diagrams to all of this in perturbation theory for the waveform. Actually, the waveform for a binary even, which is what we measure in the experiments.
And what you're doing when you're doing that is solving the Einstein equation in this guy.
Yes,
Yeah.
that's right. Yeah. Okay, so there's some universality in these anomalous dimension because all the pieces of this anomalous dimension that just come from the coupling to the mass of the angular momentum. So all these kind of quote unquote loops that just come from coupling to the mass of the angular momentum, those will be universal. I just need to know the mass and the angular momentum of the object or the energy and angular momentum, and they're the same for any object. Okay? If I have other couplings that depend on the multiples themselves, those won't be universal. So these guys, these things are in large part universal. And we'll see later which pieces exactly are universal because of this, because these couplings are just fixed in GR, right? The values of the Wilson coefficients themselves are not universal. That's the log number of a black hole is 0, the log number of a neutron star is not 0. Okay, so for those, we need to know the microscopics of the object.
Are they ish because they summed, but they're not separately universal? They sum to something universal?
No. This function in general is not universal. This function is it depends on the object. It captures precisely this response of the quadrupole moment of the object. So if I hit it with like a quadrupolar field here, and then I study like the quadrupolar emission from like a slightly later time, then that's different from a black hole and a neutron star. Yeah. Okay, so let me tell you this story about the running of the black hole tides. So the key formula that I already flashed is this one. So so there's some subtle proof of this, which again, I'm going to use this kind of quantum mechanical language because it's familiar to more people, or to some people, including me. But basically what we're using is the analyticity properties of these Green's functions and how they relate to kind of the time evolution. Okay, so we're going to look at what I call the symmetric Green's function of these operators. So basically the 2-point function of these quadrupoles coupled to the field. And this is basically like the imaginary part of the retarded Green's function, more or less. Okay, so this is kind of singling out these terms that only know about the anomalous dimension and not actually the beta function of these couplings. And then by analyticity, we know that we can continue this object to negative frequencies, right? So I'm just multiplying by e to the I pi. On the one hand, that's just a scaling transformation. So this is the dilatation operator. On the other hand, this gives me the complex conjugate of this function. Okay, just from the usual analyticity properties of Green's function, which I can write in terms of the complex conjugate of this operator. But actually, one can argue from unitarity that is related to the original operator by conjugating with the time evolution operator. Okay, so you can derive this, for instance, by imagining perturbing your dynamics by this operator. Okay, so this thing, then one can write by kind of just using like a multipolar basis. We have the kind of green, like the S matrix on one side, the S matrix on the other side. If you keep careful track of the signs of the frequency, you find that this precisely gives you this phase shift. And then the dilatation operator just tells you about the anomalous dimension. It's just telling you how this thing scales with. Okay, so it's a technical proof. I just wanted to show you there's an actual proof of this non-perturbative relation, but I'll show you that it works in a second. So it's not some like kind of unsupported claim. Okay, so let's compute this for a black hole. Okay, let's try to use this formula for a black hole to know what is the running of the multiples of a black hole. So for a black hole, we're going to look at the scattering amplitude of some wave from the black hole. Okay, so we have some like kind of partial wave expansion of these scattering amplitude. So we have this kind of phase shift and this absorption factor, some partial waves. So this is for a curved black hole. So these are some kind of special kind of spherical harmonics that know about the spin. And then this phase shift kind of receives contributions from both the near zone, so the kind of the near horizon region, and the far zone, which is very far from the horizon, which is the regime in which this EFT is valid. So we can kind of identify which terms come from where. And okay, I'll tell you how we compute this. But this kind of is the thing that tells you that we actually have a black hole. This is the thing that tells you we just have some point-like object that we are probing from far away. Okay, so this is computable in the EFT modulo these coefficients that we don't know, that we need to determine by actually comparing to this full answer. And we'll do that later. I'll actually kind of compare a calculation in the EFT with the full GR calculation and extract these tidal coefficients. But so how does this calculation go? We're just going to do wave scattering from the black hole. So okay, we have the kind of linear wave equation in the black hole background. There's this famous separation of variables in the right framework where we can write this in terms of some like spherical harmonics and some radial function, and it just turns into some ODE, which is this famous Berger-Wheeler or Cauchy equation. And typically what we do is we impose just incoming boundary conditions at the horizon and then wave boundary conditions at infinity. And there's kind of an incoming and out reflected or outgoing part, and the ratio of two tells us precisely about this scattering amplitude. Okay, this is the kind of a same as like scattering in quantum mechanics or in some 1D system. So it's a relatively straightforward calculation. And actually this equation has a name. It's called the confluent-होइन equation. And this question of relating boundary conditions at some point to boundary conditions at some other point is called computing these connection coefficients of this confluent-होइन equation.
If you have a spin, then you can get superradiance, which is not included. Yeah. Did you?
Yes. Here it's every factor is
Also
included.
superradiance.
Yeah. Here just following the full wave equation.
You can get amplification.
Yeah, that's right. Yeah. So that has to do with this factor here. So this can be greater or less than 1. Yeah. But I'm actually focusing on the phase shift, which is kind of the lasting part. Okay, so here I'm not gonna explain in detail this, but there's this kind of new tool that has appeared in the arena of how to solve this problem. So for a long time, there was this method by Mano, Suzuki, and Takasugi called the MST method, which is basically the method of match asymptotic expansion. Just solve kind of the equation around this singular point, like asymptotic series, you solve it around infinity, you require that they agree in the middle, you find the solution. Okay, but a couple of years ago, there was this nice observation by Alba-Grassi and collaborators that realized that this Regal-Tarkovsky equation is the same as a so-called quantum curve for some particular supersymmetry Yang-Mills theory. Okay, so you don't need to know what this means. You can just think of this as some kind of alien technology that comes from supersymmetrical gauge theories that tell you that there's some differential equation that appears in that context where I have particles with 3 masses and some kind of instanton counting parameter, and there's some precise mapping between this and the parameters of the black hole problem that allows like a complete solution of this connection problem. Okay. So using that technology, one can write a nice formula for this phase shift. So here I'm just showing you the far zone part, which is the one that will relate to this.
But that's still a perturbation theory, right?
No. This equation is non-perturbative.
No, but this solution is still a perturbation theory. The Nekrasov expansion is still a perturbation.
That's right. It is an expansion in this L.
So they give a name to the special function. That doesn't mean that.
That's right. Well, it's when we solve the hypergeometric equation, we also give it a name, and then we have some routine in our computer that can evaluate that numerically fast, right? So I think that's usually what we call a solution, right? But yeah, I think the power of this Nekrasov story is in perturbative expansion in this L. But these are convergent expansions, for instance. So it has some advantages here. Okay, and in particular, I will be using just for this for one specific purpose, which I'll mention now, which is okay. So here it has many pieces, this answer. So there's this kind of Nekrasov function or Nekrasov function, which is some very complicated beast. There's other pieces to the answer. There's some sort of like a Sommerfeld type factor, which is kind of Coulombic. This is the usual Weinberg phase that comes from the infrared behavior of the amplitude. But I want to focus your attention on this last piece, which has L minus nu. So this nu is what people in GR call the renormalized angular momentum. And they didn't know what it renormalizes, but they gave it that name. So it's some function of the frequency. And actually, for instance, in this Nekrasov setting, one can compute it combinatorially by relating to the derivatives of this Nekrasov function. So there's some kind of equation that tells you that this nu plus 1 is related to this Nekrasov function. That this thing can be computed combinatorially. So this just allows me to solve for this thing very efficiently, either numerically or analytically at low frequencies. Okay, so this is called the Matonner relation. Okay, but so yeah, I will just be using this Nekrasov story to compute very efficiently this nu. Okay, let me plug this into this formula. And then it turns out that there's some magic that all of this stuff, which is complicated, cancels. The only term that doesn't cancel when you take kind of this and the analytically continued version is the last term, which when I divide by this 2 pi, it just gives me nu minus L. Okay? So the anomalous dimension for the multiple moments for a black hole is precisely the renormalized angular momentum minus the ordinary angular momentum. Okay? And incidentally, this is what in the Nekrasov language is called the quantum A period of this curve. So it's something like interesting quantity also in this sense. Okay. So as I said, this nu was introduced by MST and called the renormalized angular momentum, but nobody knew what it renormalizes. And but it was actually a very good name. And now we know that actually it renormalizes the multiple moments. It's precisely the anomalous dimension of the multiple moments that tells us how it depends on how I define them. Okay, so using this technology, we can get like, okay, I already showed you the quadrupolar piece, just to show you that we can get kind of very high orders perturbative expansions for any value of L and the spin. So this is up to kind of the 6th order. And even numerically, we can play some games. So we can look at this iconal limit, where we take both the frequency and the angular momentum being large, fixing sort of the ratio, which is kind of the impact parameter. So this is a geometric optics limit. And we can resum this whole expansion into some function of this impact parameter. And it turns out that, okay, it's some expression which interestingly, it develops an imaginary part. It has the singular, but this is not, at small frequencies, it reproduces things that I showed before, but at higher frequencies, it develops some singularity. So there's some branch cut. And then that happens exactly at the critical value of the impact parameter that it corresponds to the size of the photon sphere of the black hole. Okay, so there's some non-perturbative feature of the black hole that one can see in this running of these multiples. And actually, if people compute this renormalized angular momentum numerically also, and one sees a similar behavior.
So what does it mean that it's imaginary? Do we get exponential amplification?
Okay, it depends on which quantity you're looking at, but typically you get some oscillatory behavior.
Oh, so it's never exponential.
Yeah, because it's a real exponential, it's not an imaginary exponential. And I'll show you the waveform in particular, how this affects the waveform. Okay, so this is something. So this quantity is interesting. It knows somehow about it knows about that something interesting happens on the photon sphere. Okay, I don't have much more to say about this at this moment. Okay, because going back to this question of universality, I told you that everything that depends only on the coupling, linear in spin or to the energy, to any order in the energy, is universal. So what does that mean? If I expand this function, so this is omega, this is kind of omega times the spin. If I expand it at small spins, then the leading order, which is basically this kind of renormalized angular momentum for Schwarzschild, and so here I'm taking the full answer for a curved black hole, and at linear order in spin, then these two terms are universal and they're the same for any compact object. actually not even in any compact object, anything that we describe by like a point particle coupled to GR long distance. Okay. And everything that depends on spin squared or higher, it's not universal, so we cannot say anything about it. Okay. So so using this, we can resum logarithms in various quantities of interest, and even propose some kind of non-perturbative improvements to models that we have for wafers. So let me show you these applications, or a couple of applications. Okay, so one setting in which one uses this point particle theory is when we compute the radiation from the binary itself. So when we compute radiation from a binary, we're computing the radiation in this far zone. So this frequency is kind of much smaller than the inverse separation of the binary. Okay? This is what we actually measure at LIGO. And so what we do is we replace this binary by a point particle with a given energy, angular momentum, and multiple moments. Okay? So for instance, the famous Einstein quadrupole formula is valid in that framework, where we are in this low frequency expansion, and we're looking at kind of the leading emission, like the leading flux of energy, which is due to the quadrupole. Okay, the quadrupole of the binary itself. Okay, so in particular, I showed you earlier that there were these logarithms in the waveform. So we can resum them using these anomalies I mentioned. So here, nu I'm calling L plus the anomalous dimension, and this is actually what we measure in when we look at the gravitational wave, the actual waveform as emitted from this binary system. And so for quasi-circular binaries, this allows us to propose kind of a formula that resums all of these logarithms. So there was an earlier version of this formula in 2009 by my colleague Thibaut Damour and Alessandro Nagar, where it just resummed the infrared logarithm. So there's also some infrared tails that were resummed, which is essentially the same formula without this term, and we replace nu by the ordinary angular momentum. Okay, but by doing this simple replacement, then we can also resum all these other logarithms that appear in the final answer. Okay, and actually the problem disagrees with certain calculations that people have done, and the interpretation of this is very simple. The interpretation of this is that we have this quadrupole or like multiple radiation from a binary system. After this kind of gravitational wave is radiated from the system, until it reaches us, it's just propagating in the background, which is sourced by this binary. And the most important thing is the energy of that binary and the angular momentum of the binary. So it's kind of propagating in the kind of Schur-Schild with this length-Turing correction spacetime that is sourced by this binary, and that's completely universal. That doesn't depend on which object I'm looking at, if I know its mass and spin. Okay. So we can go and check this against, say, perturbation theory. And so this is kind of the state-of-the-art prediction in this post-Newtonian setting of the kind of quadrupolar waveform, actually from a binary, from Luc Blanchet and collaborators. This is something from a couple of years ago. Now they have the 4.5 PN. I didn't add because there's nothing new there for this resolution. And all the terms that I showed here with a box are terms that are predicted with their precise coefficients by this formula that I presented before. Okay, so without doing any calculation, this x is basically the omega, is the frequency to the 2/3, which is the usual post-Newtonian parameter. This is related to the kind of size of the orbit. And so all of these logarithms will sum in a bunch of kind of factors of I pi in the phase and even some finite pieces in this answer. Okay, so this is kind of a check that our resummed formula works in this perturbative setting, which is just post-Newtonian perturbation here. And actually, we've checked against all the state-of-the-art calculations of all the multiple moments. And again,
sorry, those are the things in the red boxes.
Yeah. So all of that is contained in our formula, including all these logs. There's an extra logarithm here.
What about
The
the,
red box are the
So
post-Newtonian.
all of this is the post-Newtonian.
so what about the rest? You're not accounting for them?
The rest are like finite parts that are not universal. So these parts are completely universal and is what we can predict. But these others, you actually need to solve for the dynamics of the binary. So there's this kind of H finite here that we cannot predict. But for instance, that is free of all these tail logarithms. There's some extra logarithms that I can discuss later, which they're related to some effect, which is called the tail of memory effect, that I can tell you about, which is not, a black hole doesn't have this tail of memory. That's why we kind of resum it. But okay, we can talk about that later. Yes.
Well, suppose I don't know what the H finite is.
Yeah.
Can I I was given this formula. Can you give like a procedure to tell which term corresponds to the universal P?
Yeah,
from
so
this
for instance,
formula?
everything that comes with a pi or an a pi or gamma Euler or a log, we resum.
Okay,
And everything which is just rational numbers, or, okay, so here there's some corrections that go like the mass ratio, then some of them be more subtle. So pi squared corrections, some of them we can capture and some of them we cannot. But the ones that we cannot capture, they're not universal. So if you change some parameter, for instance, they're not the same for like a quasi-circular binary and a generic binary. Whereas
What
this
about
form,
that pi squared? There's a pi squared. Oh, so it's not a transcendental expansion you're doing.
this is just an expansion in small a.
There's some with pi squared there,
There is even one with pi.
Yeah, there's also terms with just one pi and I pi.
but those are in the boxes.
No, there is one that is not.
Uh,
Oh, you're right, you're right.
down here, yeah, because that has to do with this tail of memory log, which I can comment on later, which we couldn't resum because it's not universal.
So it's not like this transcendental expansion people do it here.
No. This is literally a small x expansion. This answer, which is what people compute for the inspiral. Yeah. So for instance, this describes the actual signal during the whole inspiral phase until this x becomes too large, which is kind of a few orbits before the merger.
So usually we would say that the constant pieces are not universal because they can mix with the other constants.
Yeah.
So you need to somehow disentangle the log.
Yeah, so some of them
sides.
are because these I pi's are tied to the log.
Mhm.
Also, the gamma Eulers are tied to the log. The others, it's a proposal based on this picture of waves propagating in this background. So there's a real part of this kind of gammas, which is not just kind of a prediction from RG, but it's more kind of a proposal that we have. Yeah. But all the logs is a proof, like we have
Right,
a
so-
proof from this RG that we can resolve.
So sometimes you can have some prescription of how to extract the universal by taking
Yeah.
some derivatives. So probably you can do
Yeah, so
something
for instance,
similar.
there's this famous
Yeah.
Sommerfeld factor when you have some low
Yeah.
velocity scattering, which is like a part of the real, like a real part of the amplitude,
Mhm,
which we know it's large
Right.
and that it can be resummed. So you can think of the real parts that we
Right.
resum as this kind of Sommerfeld type
Mhm,
of resolution.
mhm.
But now instead of one over our potential, which is what people do say,
Right.
that
in-
matter or
yeah.
something, it's for the full kind of short shield background,
Mhm, mhm.
yeah, with this linear spin correction.
And what about numerics?
Right, so that's what we are working on right now. So I won't show any. So we are in the process of trying to compare to some like numerical GR predictions. But unfortunately, the numerical GR predictions, they cannot give you like a kind of many cycles for this inspiral phase. So we are kind of pushing like both these perturbative expansions and what we know about the waveform. Because if you want to compare to the regime where GR, like NR is very good, you need to get pretty close to the merger, and then you need to know these pieces. So the comparison is actually not completely straightforward.
In LBK, are they mostly comparing to numerics or to PPR?
So in experiments, they compare to these waveform models,
Yeah.
which are kind of a patchwork of all of the approaches. So there's some like analytical prediction that comes from these perturbative calculations. There's some like resummation procedure. For instance, there's this effective one-body model, those that were pioneered by my colleague Damore and Alessandro Bonanno. And then they tune those to NR, and then that's what's used. But it's not like a first principle prediction. So the only first principle predictions we have are the few NR kind of fully evolved waveforms that we have, but those are not in the hundreds of thousands, which is what the template banks are. What we need for these templates to kind of do detection, et cetera, et cetera. So now it's everything goes to these intermediate models, which are kind of a combination of various things, but they're not really like a first principle GR prediction.
Well, it all comes from GR, right? You might feed GR to your.
Well, it agrees with GR in any regime where you can expand, and in the particular numerical settings where you have tuned the model, but beyond that, there's no guarantee. It doesn't actually make up like a first principles prediction, right? It's a model. It's not really like a calculation from GR. The only full
I don't understand that. I thought the simulations were trying to simulate GR. They might not be perfect.
No, the
because-
simulations are fine. He's talking about one body approximation.
Yeah. So but the simulations is not what is used because we have very few simulations. So yeah, you can put GR on a computer for comparable masses,
Right.
run it for like many hours, and then get a full prediction for a few cycles. So for instance, for like, yeah. And so those are the only kind of first principle predictions we have of fully evolved waveforms. But for instance, these extreme mass ratio regimes, NR cannot predict that. Maybe to mass ratio up to 10. So actually the experiments rely on these models, which are not first principle predictions. They work extremely well. So whenever we compare to NR, they agree, but okay, that's also where they've been tuned. Where we cannot simulate GR in a computer, we cannot compare against anything. Yeah. But this is the, I mean, this is the truth. So this is actually a perturbative expansion in GR, right? That we are comparing with. So this is an actual prediction from GR. It's not has nothing to do with the model that then goes into the kind of detection and yeah. Okay, so we can also like resum logarithms in various quantities. Like for instance, if you look at the gravitation, like the flux of energy in the form of gravitational waves, it also has all these logarithms. So the first two were computed. Now we have like 10 more orders in the frequency expansion. We can resum all of those. Some of them are only known very recently. There's other logarithms in these quantities, like there's these IR logs, there's conservative tails, there's these tail memories. Those, they don't correspond to the anomalous dimension of the multiple. For instance, they correspond to the beta function that I mentioned. Those we don't have some universal all orders prediction. So we cannot do everything, but we can at least resum part of the answer, and hopefully it will lead to some improvement in our predictions. Okay. Another application is that actually this RG is important when you try to model the response of a neutron star. So this is from a paper about 10 years ago, where they compared the actual kind of response for some like polytrope model of a neutron star with like two like resonant frequencies. When you have, okay, so here's one, here's the other, and then if you just try to fit this model against kind of numerics, then it doesn't work very well. So these are these kind of white points here. And then if you just do the leading RG, it doesn't work very well. But when you resum this leading RG, actually you can get a very good fit for these models of the neutron stars. So actually this normalization loop running is important when you're actually trying to understand other objects, not only black holes. And as I mentioned, a lot of it is universal. So now we know a lot about this running. Okay, what if you don't care about classical GR and gravitational wave physics? What if you care about quantum black holes? Okay, so this point particle EFT also has some implications there. For instance, there's this interesting paper a couple of years ago by Wald and collaborators, where they showed that kind of black hole horizons can decohere superpositions in quantum mechanics. And then there was a recent paper by Biggs and Maldacena, where they show that actually it's not special about black holes. If you have any object that has this kind of dynamical tidal effects that have to do with some terms in this two-point function of the multiples, that leads to the same effects. Okay, so black holes are just kind of ordinary quantum objects, and just kind of ordinary dissipation is enough to decohere kind of qubits which are in contact with this black hole, with whatever object. Okay, there's also some interesting papers by Goldberg and Rustin where they can compute the effects, kind of universal predictions from GR, or kind of virtual like Hawking quanta. So this is not the Hawking quanta that escape to infinity. That is what the usual Hawking calculation gives you, but these are kind of Hawking quanta running inside of loops of some calculations. So for instance, they compute some prediction to the cross-section for point particles in gravity, which is universal. It's a long distance prediction. It's a prediction of quantum gravity and it's comparable just to the ordinary loops of gravitons. Okay, so there's other things that one can do with this EFT. This is just advertisement for this EFT, which I like very much. Another setting where this EFT can be useful, okay, so maybe you care about holography. So the kind of analog setting of comparing a point particle to something like a full black hole. It's typically when people compare kind of correlation functions of light operators in the presence of heavy operators in ADS CFT with things like the thermal two-point function of these light operators. So here the bulk picture is okay, some thermal state, you have a black hole and you have waves propagating in this background. Here you have kind of a very heavy particle moving along some geodesic and waves interacting with this heavy particle. Actually, the EFT, for instance, predicts to which order in 1/n you expect that these two quantities agree. So people have computed into leading order. You find an agreement between the two, but that actually will break down at some point because this heavy operator doesn't necessarily need to correspond to a black hole. Okay, so this is a summary of the running part of the talk. So I realize I'm already out of time.
You're
So,
running over time.
Yeah, I'm running over time. So maybe let me just flash what I was gonna show next, which is that we can also extract these log numbers. So very quickly, the usual calculation, it was this linear response calculation where one solves this kind of static radial equation. But actually, there's a bunch of ambiguities when one tries to do this for dynamical tides having to do with various gauge ambiguities in GR. So actually, there's a nice approach, which is we can, again, use scattering amplitudes to extract these quantities. So we can compute scattering of waves against a black hole in black hole perturbation theory compared to the same quantity in this point particle EFT. And this scattering amplitudes are nice gauge invariant kind of field, coordinate independent quantities. So these are free of all of these ambiguities. Just a comment, there's been previous attempts in the literature which in fact ignored the fact that in this EFT it's fundamental to compute the correction from these nonlinearities, these loops. So they were trying to match kind of three-level expressions for these amplitudes to black hole perturbation theory, but that doesn't make any sense because kind of the EFT expansion parameter and the loop expansion parameter, they're comparable for black holes. So one needs to compute all these nonlinearities, and actually that's what we did. This is the answer from BHPT. So, okay, we did this for a scalar because it's a bit simpler. So let me just show you the answer. So this is the phase shift from black hole perturbation theory. This is what it looks like, the final answer, say for the L equals 0 case. And if we add both the near and the far zone, there's like a good prediction with this physical log, with RS inside of the log. If you compute the same quantity in the EFT, for generic L, you agree, where there's no contact term ambiguity. But for L equals 0, where one has at this order in the low frequency expansion, the first dynamical tide appearing, then there's a UV divergence as predicted, there's an ambiguity, but we can just ask that they agree, and that lets us extract precisely the value of this dynamical tide in GR. Okay, so that was very fast, but the idea is that we can just compare two calculations. One is I mentioned the UV complete theory, which is black hole in GR, scattering waves from it. The other one is scattering waves from a point particle in GR with nonlinearities, and then we can extract these numbers unambiguously from these calculations. Okay, and there's some group that has reproduced this, and actually they can go to very high orders for the scalar case. So this is where we stand in this story. So we've done to kind of third order kind of RSQ, which is essentially as hard as a two-loop calculation in perturbative GR. And we've done it for scalars, photons, and graviton waves, so kind of spin 0, spin 1, and spin 2. And from that, we extracted the leading dynamical tides for the scalars. Unfortunately, the leading dynamical tides for the gravitons enter at order IS to the 7, which is like a 6-loop calculation. Okay, so this other group that I mentioned, they're already here. I think we can eventually get there, which is what we want, because, for instance, these enter at the same order as the octupolar tides. For the actual observables in light. So the goal is to be able to compute these two for gravitons so that we can actually analyze their effect on the waveforms. Okay, so after that very fast comments and matching, let me just conclude here. So I showed you that there's some relation between this running of the tides or these multiple moments and kind of scattering amplitudes or scattering phase shift in GR. Actually, this formula is not particular to black holes. Actually, so there's a powering universality because black holes is a control setting where we can compute the right-hand side very nicely and then extract some universal predictions from the left-hand side. But this formula works for any object. So if you actually have a binary, it tells you that if you kind of scatter waves, gravitational waves from the binary, you can compute the right-hand side and really tell about the kind of non-universal running of the multiple moments of a binary itself. So I think this gives a new target for kind of predictions from GR people, which is kind of computing scattering amplitudes from actually a binary system that might give some kind of non-perturbative upgrades to waveform modeling, like the one I presented, where we sum all of these logarithms. And okay, and also we have all these tools from scattering amplitudes and QFT that we can nicely use to analyze this classical GR problem and make some progress. Okay, and I'm here.
We can take a few more questions. Is there an electromagnetism version of this EFT as well, where instead of GR you couple to some strong field electromagnetic setup or something.
Yeah, in electromagnetism is a bit boring because electromagnetism is a linear theory. So you have that self-force divergence, which is a power divergence. You don't have these logarithmic divergences.
I see.
So it's kind of boring.
I was imagining in that setup, you could try to do some quantum calculations as well. Because you would have.
Yeah, even there won't be these
Them.
point particle logs. It will be something else. Yeah.
Didn't like Alex Ridgway do the like QCD answer where you have color factors with the Yang-Mills coupling?
Yeah,
That's
so
not
actually
here.
what's unclear is in which setting one has this kind of classical picture, which is kind of a large occupation numbers type of. So the only picture that I know where there's some like classicality going on that maybe kind of is amenable to this kind of analysis is this kind of color glass condensate that they use for like heavy ion.
Yeah,
So there you have some classical glue field, which is perturbed by small things, which is sourced by this quark-gluon plasma. And okay, it's a very different setting. So that's why we don't have like colored point particles coupled classically to Yang-Mills. Yeah, so yeah.
Okay, we had enough questions during the talk, so if there are no further questions, let's try to speak again. We'll